Hello. Last time we talked about applications of the first derivative. Today we're going to talk about applications of the second derivative in 4.2. We start from considering the graph of the function f in two different situations. On the left-hand side, the graph of the function f is opening up, and we call the graph is concave up. On the right-hand side, the curve is opening down, and we call the function is concave down. On the left side of the graph, when x is less than c, the function is decreasing, so the derivative is negative. At x equal to c, the derivative is 0, and as x is greater than c, the derivative is positive because it's increasing. So if we consider the derivative of f prime as a function itself, then it increases from negative to positive from left to right as x increases. So that means the derivative of the f prime is positive because it's increasing. But the derivative of derivative is the second derivative. So we conclude that the second derivative is positive. That means we can use second derivative to determine the concavity of the function. When it's positive, then the function is concave up. Similarly, on the right-hand side, the function is increasing as x is less than c, so f prime is positive. And at x equal to c, f prime equal to 0. As x is greater than c, and the function is decreasing, so the derivative of f is less than 0. So in this case, the derivative of f decreases from positive to negative, from left to right, as x increases. So that means the derivative of the f prime is less than 0 because it's decreasing. But again, the derivative of a derivative is the second derivative. So the second derivative is less than 0 in this case. So when the function is concave down, the second derivative is negative. So we can use the second derivative to determine the concavity of a function. And we just follow the 3 steps procedure. Step 1, we find the x values in the domain of f for which f double prime equals 0 or f double prime is undefined. And these are candidates of so-called inflection points of f where the function f changes concavity. So we're going to find all the x values when f double prime is 0 or f double prime is undefined. And when the curve or function changes concavity, then we call the points inflection points. Step 2, identify open intervals determined by the values of x found in step 1. So we use those values in step 1 to divide the domain in different regions. Step 3, we just check the sign of double prime, f double prime, and determine the concavity of the function in each interval. So let's do a simple example. Let f(x) equals x cubed minus 3x squared minus 24x plus 32. Determine where the graph of f is concave up and where it is concave down. So just follow 3 steps on the last slide. So in the first step, we just take the second derivative. So the first derivative of the function is 3x squared minus 6x minus 24. And the second derivative of the function will be 6x minus 6. And we set it to 0 and find 6x minus 6 equal to 0, so we get x equal to 1. In step 2, we divide the whole domain into 2 regions by the point of x equal to 1, namely the negative infinity to 1 and the 1 to positive infinity. And in each of those intervals, we just pick any value of x to check the sign of the second derivative of the function. For example, in the interval from negative infinity to 1, we can pick x equal to 0 and find the second derivative of the function is 6 times 0 minus 6, which is negative 6. So that's negative, so f is concave down. Similarly, in the second interval from 1 to infinity, we can pick x equal to 2. We got f double prime of 2 equals 6 times 2 minus 6. So that's equal to 6. And that's positive, so f is concave up. So at x equal to 1, the function changes concavity from concave down to concave up, from left to right. So x equal to 1 is the inflection point of f. And now let's talk about the second derivative test for locating extrema of function. We discussed the first derivative test in 4.1 to find the relative extrema of a function. Today we're going to discuss the second derivative test, so that's a different method. Let's just go back to the graphs on the first slide. On the left, we got the curve opening up or concave up. At x equal to c, we got the minimum, where the derivative, or first derivative of the function at x equal to c is 0, but the second derivative of the function at x equal to c is positive because the whole curve is concave up. On the right side, we have a relative maximum at x equal to c, where the first derivative of the function again is equal to 0 at x equal to c, but this time the second derivative of the function is negative because it's concave down. So we can use the sign of the second derivative at the critical numbers to determine whether it's relative maximum or minimum. Okay, so this is called the second derivative test. We just need to follow 2 steps. Step 1, find all critical numbers, that is values of x, where f prime equal to 0, f prime does not exist, as we did before. Step 2, test signs of f double prime at the critical numbers and identify extrema of f. So let's just do one example. Let the f of x equal to 2x cubed plus 3x squared minus 12x minus 4. Find the relative extrema of f using the second derivative test. So in step 1, just take the derivative of the function. We got the 6x squared plus 6x minus 12, and put that equal to 0 to find the critical number. So we got a 6x squared plus 6x minus 12 equal to 0, and we can factor the left hand side to get the 6 times x plus 2 times x minus 1. We solve the equation to get the x equal to negative 2 and x equal to 1, 2 critical numbers. In step 2, we just find the second derivative function. We got 12x plus 6, and then check the sign of the second derivative function at the 2 critical numbers. So at x equal to negative 2, we got the f double prime equals 12 times negative 2 plus 6, which is negative 18, so that's negative. So we got the relative maximum at the x equal to negative 2 because the second derivative is negative. At x equal to 1, we got f double prime 1 equals 12 times 1 plus 6, and that's 18, so it's positive. So f attains a relative minimum at x equal to 1 because the second derivative is positive. So that's the end of today.